Check, 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 sound, check, sound, sound, sound. Sound good? Do you hear me? I don't hear you yet. Anybody hear me? There we go. Anything fun happening this weekend or happened over the weekend? Oh, yay. Oh, their first time in Berkeley? Did you guys get to second? Did you get to tour around? It was pretty nice weekend, a little bit foggy. Where'd you guys go? Did you go across the bridge to the city or hang out? Yeah. Mm-hmm. No way. Was it cold and windy, foggy day? Yeah, it's almost always windy. Yeah. Alcatraz is fun. You should do it while you're here. It took me forever to do it. I think, let's see, I was in grad school I was in grad school because Wendy was involved. She went, and she's a native of California. Where was she from? Pretty local, but I forget exactly where. But we used to be able to go to her house, and she had never been, so it was the locals never go to Alcatraz. We went to Fort Baker, which I totally recommend. So that's on the other side base of the Golden Gate Bridge, right up at the very base of the Golden Gate Bridge, below it. So you look up and up to the Golden Gate Bridge from the shoreline. Spectacular view. Holy crap. There's an old army base that's been converted into a conference center there. Oops, my mic was on. Pretty close. Okay, are we 8 o'clock? Good morning, everybody. Welcome back to Berkeley, California, 208 Stanley Hall. That's where we broadcast from. Hopefully, all you will come and visit. Please do come and visit when you come back to Berkeley. Look me up. When do classes start in the fall? The 28th, 29th, 25th. So most of you will be heading back soon after the final, if you're regular Cal students. If you have not already, fill out your course evaluation. So you got an email, and we posted an announcement with the link to the course evaluations. We'll send out another one this morning with some information about the final coming up and what we're doing for that. The course evaluation are taken very seriously, so your comments are all tabulated by our departments, and they are literally used to decide who teaches what courses and what happens in the department. And for this particular course, I think I've said this before, we'd love to have you comment on that. So I added, I'm allowed to add specific questions to the course evaluation beyond the the set ones. So there are some places at the bottom where you can say, just free response. What do you feel about how this works? And what was your learning experience like compared to other online classes that you've had? This is new to all of us. We're just in our in COVID enforced second semester of doing this. So we're trying to improve, and it's given us the motivation to improve for posterity, for perpetuity. So we're good at this moving forward. Those of you that have been at Cal know that in 2018 we were shut down because of the fires, and we had to stop then and try to get instruction moving. That was very difficult because we weren't anywhere near prepared to go online. So everything you can say, feedback, suggestions for better, comments on what doesn't work are very helpful, of course. So please be honest. We can't see any evaluation comments that you make until after final grades are submitted, quite a while after. They make us wait. It's something like, I don't think I can see until fall starts even, but I look forward to seeing what you say. So please don't hold back. Honesty is the best policy. So we've been talking about weak acids and bases, and last time we came up with a very interesting observation, and that was that if you dilute a weak acid, first we diluted a strong acid. We diluted HCl by a factor of 10, hydrochloric acid by a factor of 10, and it went from pH 3 to pH 4. So 1 order of magnitude. Factors of 10 in science we call orders of magnitude. So 1 order of magnitude change, 1 pH unit is a factor of 10. We know that's a log base 10 scale. So 1 pH unit, 10 times in concentration, and that was an exact change from pH 3 to pH 4. Then we looked at the weak acid, and we found out something that was a little unexpected to start with, and that was if you dilute a weak acid that's pH 3, if it's pH 3, that means the H3O concentration is 10 to the minus pH, 10 to the minus 3. So you should be able to write that now confidently. But in order to get pH 3 for hydrochloric acid, you just put in 0.3 moles per liter. I'm sorry, 10 to the minus 3. I did that again last time. This is 0.0001. So you put in 1,000th of a mole of HCl. If you put in 1,000th of a mole of acetic acid, you would get barely any H3O plus at all. This is a weak acid. This has K less than 1. And we know it's around 10 to the minus 5 now. So that does not go very far. So you have to put a lot of HAC in to get to that pH 3, much more than 1,000th of a mole. And because you have to do that, when you dilute it, there is HAC, there's a lot of HAC in solution. And that dissociates further. As the volume increases, it's like a gas expanding to fill the volume. This goes in that direction and makes more H3O plus. So the pH goes from 3 to 4 immediately when you change, when you dilute it. But then as equilibrium is attained, more of this dissociates and it comes down from 4 slightly. Not all the way back down to 3, but lower than 4 because you get a little more dissociation of the weak acid. So the fact that the weak acids they hold back. There's this reservoir of protons there that the strong acids don't. The strong acids totally dissociate. There's no hiding what's going on. That reservoir of protons is what makes weak acids interesting, and it's what creates buffer solutions, which is what we're going to talk about quite a bit more today. So pH somewhat less than 4 for that. So here's the titration curve that we've been talking about, and we've talking about the reaction of a weak acid. So we start out at a weak acid pH when that's all we have in solution. And then we add a strong base, and for every mole of strong base, that reacts with 1 mole of weak acid and forms water and the conjugate base. So the strong base just essentially finds the strongest acid in solution. There's a lot of exchange going on, but the equilibrium finds that the strongest acid in solution reacts with the base. And even though this is a weak base, it's a weak acid, it's a stronger acid than the water that's there. So the proton preferentially comes off the HA to form water and A minus. There's a lot more water there, but there's equilibrium is occurring. So those protons are jumping on and off. And once this reaction occurs, that is quite a weak base, so it doesn't go back in this direction. So there's a tendency for this to build up. So we say at equilibrium, one of those finds one of those 100% and turns it into one of those. Why do we say 100%? Because going back in this direction, that K is extremely small. That's the base reacting with water. And that K going in that direction is the KB, for that conjugate base. And if this Ka is around 10 to the minus 5, then that Kb of the conjugate base is 10 to the minus 9. Remember, they have to multiply 10 to the minus 5th times 10 to the minus 9 to get 10 to the minus 14. Ka times Kb is Kw. So going in reverse is very unfavored. So stuff is stuck over here. So you have a strong driving force, thermodynamic driving force. The equilibrium favors this side. So every mole of base you put in gets converted to the weak base from the weak acid. So that makes the titration curve easy to calculate. You start at one of these points, A, B, C, D, and calculate the pH based on the appropriate equilibrium that's occurring. So we did pH last time with acetic acid, and we found the initial pH was around 3-ish, 2.8. So if this is acetic acid, initial pH at about 0.1 molar was around 3, 2.8. Now we're going to look at region C, and region C, we're going to skip by B for a minute, come back to that. Region C, that's the equivalence point. And you need to know the names of these points on the titration. Of course, the initial point, we'll call this flat area the buffer region. The equivalence point, where you have added now a mole of strong acid for every, a mole of strong base for every mole of weak acid that was there to start with. So you've used it all up. And you converted all the HA into A minus. Now, again, we say all, but of course, it maintains an equilibrium. So even though going back is 10 to the minus 9, K 10 to the minus 9, some does go back. But most of it stays here. So it's a solution of a weak base. So here it was a solution of a weak acid, and now it's a solution of a weak base. So let's look at that. Let's say it's the weak base, and that will form an equilibrium with water, because that's all that's there now. These two, all your OH minuses were used up, and all your HAs were converted into AC minuses. So that and that is what's there, and those will come to equilibrium. So we say, well, let's start here and figure out what that pH is. So initial conditions are all converted to this, and then let's see what dribbles back to HAC. So I write this down, and this is the classic HAC reacting with H2O to form HAC and OH minus. And that's the classic weak base. So that acts as a base, accepts a proton from water, makes the conjugate acid and the strong base OH minus. And here are the forms. So this is the acetate ion, AC minus, looks like this. This proton is the acidic proton. The hydrogens on the carbon do not come off. Their pKa's are huge, in the hundreds. Well, no, they're not in the hundreds. Well, they might be. That pKa, we know that the bigger the pKa, the weaker the acid. So these pKa's are ginormous. This pKa around 5-ish is in the weak acid range. K 10 to the minus 5 if pKa is 5. This is a weak base, so its pKb, which is what we want to know for this, is around 9. Since it's a weak base in water, we expect the pH at equivalence point. This is where we are, the equilibrium, the predominant equilibrium at equivalence point. You've converted 100% of your acid to base. That pH, we would guess, is going to be in the basic range, bigger than 7, but less than 13 because it's a weak base. So let's just say we have our 0.1 molar-ish AC minus now, and that dissociates a little bit. So I'm not writing the ICE, I'm just writing out the equilibrium concentrations. You lose, are we autofocusing? You're not getting a light. How's the focus right now? Sharp? Okay, let's let it focus. Here, I'll force on autofocus. Did the board get sharp? Okay, let me step out of the way. Did it focus? Okay. Is the board sharp? Let me force autofocus. If I walk around, does it focus? Okay, stand by, guys. We're having trouble with the camera focus. I can focus it on the board manually. Stand by. Is that getting better or worse? Worse. Other way. Come on. I think it's going. Nope. There we are. Okay. And that should be stuck on manual now. Okay. Apologize, guys, for the lack of focus. Sometimes you guys have a lack of focus. I come to the Zoom rooms and there's so I have no idea where I was. Okay, so this is the equilibrium situation now. We converted all our weak acid to base. So this was about the concentration originally of the weak acid, but now it's been converted to base. A little of that dissociates and makes a little of that and a little of that. And a little of that is what we want to know because that will tell us the pH, the OH minus concentration. So let's solve for X. We say, well, that's an equilibrium expression. Let's write products, X times X, over reactant concentrations. Water does not appear. Set that equal to K. And the KB, as we were saying, is around 10 to the minus 9. That's the exact number, 5.68 times 10 to the minus 10. And solve for X. We solve for X using an approximation to make the math easy. So we don't have to solve the quadratic with two terms. We just have to use the quadratic term itself. And this assumption that X is so small that subtracting it from 0.1, we wouldn't know the difference. The number is still so close to 0.1 that you might as well just use 0.1. So when we make that approximation, we get x is 10 to the minus 6. And yes, this is 10 to the minus 1. So indeed, x is 10,000 times smaller than 0.1. So it's a good assumption. X is 10 to the minus 6. And that now is the OH minus concentration. I can get the H3O plus concentration from that, because if you take nothing else home from Chem 1, take home the fact that that concentration, OH minus, times H3O plus, has to equal 10 to the minus 14th in water all the time at 25 degrees C, no matter what else is happening. All equilibria are satisfied simultaneously. So the pH is 8.8, and I don't have the math there, so I will emphasize, how did we get there? This OH minus is this number. But OH minus times H3O plus, that's the number I need to get the pH. Their product is always 10 to the minus 14 in water. So plug in 10 to the minus 6 here, and you can see you would get something like 8. 10 to the minus 6 times 10 to the minus 8 would be 10 to the minus 14. So you get something like 8, and you say, yes, the pH is going to be around 8. Use the exact number to get your pH with your calculator, but you can do it in your head with just the exponents. Okay, so that makes sense to us. The pH, and take this to the bank, the pH at equivalence point of a weak acid solution is not neutral, because you have weak base there. So it's not pH 7. It's pH 8.8, almost 9. Okay? Take all those things home. So consider the titration of the following with a strong acid or base. So if one of these is an acid, consider titrating it with a base. And if it's a base, consider titrating it with an acid. For which is the pH at equivalence point less than 7? Oh, okay, we can do this. I was thinking we needed more information, but we can get an approximation. All we need to know is it less than 7. So is the pH acidic at equivalence point is what we need to know. Less than 7. So we don't need to get a number. We just have to, is it bigger or less, higher or lower than 7? And I've given you the pKa's. And for HCl, HCl is a strong acid. And remember I said, if it's a strong acid, number one in the exam, I'm just going to tell you, but we don't generally write a pKa because they're huge. So if your pKa is minus 7, then your K is 10 to the plus 7. So that's a huge number. It's so large, it doesn't make sense to do equilibrium calculations. That's not an equilibrium. It lays so far to products. K is so large that it's essentially all H plus and Cl minus. These, we have to do the equilibrium calculation. Ka here is 10 to the minus 3. Ka here is 10 to the minus 5. We've given the pKa's. So let's walk through this one together. Excuse me, let me sip some tea. Thank you. So the species that are present at equivalence point, what is there at equivalence point? Well, HCl, if you're titrating that with a strong base, because that's an acid, all your H pluses will be converted into waters. You'll have an H plus react with an OH minus. So this is going to react. This gives you H plus plus Cl minus, and we're saying essentially 100% because that K is so large. And then you add a strong base. We're going to titrate with OH minus. Where this came from, I don't really care. Maybe sodium hydroxide, NaOH, is what you added. But those guys react together. And when those guys react together, that K is enormous, even bigger, 10 to the plus 14 for those two guys reacting together. So that also goes to completion and leaves you water, H2O, and Cl minus in solution. Okay, so what's present at equivalence? Cl minus and water. Is Cl minus going to affect the pH? No. Why? It's the conjugate base of an extremely strong acid. So going back in that direction does not happen. That's what strong acid means. It goes all the way in this direction and it stays there. So there is no good base in solution, and that's why strong acid, strong base titrations, the pH at equivalence is 7. That's the strong acid, strong base condition. Here's a weak acid. That's not going to be pH 7 at equivalence point. Why? Because now this, you remove all those protons with your strong base. And now this is what you have 100% of in solution, but that's a weak base, so it goes back and there's an equilibrium there. Don't really even have to know exactly though, because what you're saying is at equivalence, you have a base. So if equivalence, you have a weak base, the pH is going to be bigger than 7. We kind of did that just a minute ago. We found for acetic acid, it was almost 9. We're not going to do the calculation. We just know it's basic. And then this is a weak base. So I'm going to titrate that with a strong acid. So to this one, I add H pluses. And those H pluses react with that. So at equivalence, all of those react with the acid that you've added, 1 mole of that for 1 mole of that, to form NH4 pluses at equilibrium. And that is a weak acid because it came from the conjugate weak base. So at equivalence point for the last one, C, what you have in solution is a weak acid. So that pH will be less than 7. So this is the one that has pH less than 7 at equivalence point. Okay? Essentially, it just matters what is there at equivalence point. When you titrate an acid, you convert it into a base. So it's going to be a basic solution. When you can titrate an acid with a weak base with a strong acid, you're left with the conjugate acid at equivalence point. So smaller than pH 7, higher than pH 7. Acidic, basic, at equivalence point. Not neutral, not pH 7. Okay, let's calculate the pH of 100 mils. We'll just do a calculation. It's helpful to do these calculations because there's a lot of steps to them. In the fall, I don't do this. I don't go through calculations. I let your GSIs do them in office hours, and you've got your worksheets. You go through these kind of things. But summer happens so fast, I kind of take a little bit of mercy on you, and I use up a little lecture time. Use up a little lecture time to do a calculation. Normally, we offload that to discussion time. But things happen so fast, and this is the last week, and you've got a lot to absorb even in this last week before the final. And for the final, you have to know everything. It is completely cumulative. You're not going to find any finals at Cal that are not cumulative. Everything is going to be covered. The last stuff, a little more emphasis because you haven't seen it yet. So if I have the weak acid in solution at 0.1 molar, and I'm going to add 5 mils of a very strong base, sodium hydroxide, 5 mils of that, 1 molar, quite concentrated as well. This is the equilibrium I'm interested in because I'm converting that to that. So what is this position of this equilibrium after I've added strong base? So initially I would say, well, 0.1 molar, I'd start with 0.1 molar there. So let's calculate how many moles are actually there of HAC. Molarity times volume, moles per liter times liter is number of moles. So there are 0.01 moles of acetic acid there. That's going to react mole for mole with the strong base. So how many moles of strong base? 5 milliliters, 0.05 liters times 1 molar is 0.05 moles of strong base. Those react together 100% and make this. So I can just subtract. So at equilibrium, I have 0.005 moles of AC minus that I just made, but there's also the HAC left over. I didn't use up all of it. In fact, I've gone kind of halfway. I've added half as many moles of strong base as I needed. Half of my original acid is converted into base. So at what I can do is set up this equilibrium, but just say those concentrations are equal to start, and then ask what the pH is. Remember, every point on the titration curve is at equilibrium. So you add, you say, what do? I add acid base. I get to some point that I can plug in numbers and calculate the equilibrium. So the pH is after equilibrium occurs. Once I get to half a mole of each, after equilibrium occurs, that's the point on the titration curve. Every point on the titration curve is at equilibrium. And you know this already. Equilibrium is established no matter where you come from. You can start at any arbitrary point and use this calculation to get to equilibrium. We just pick a convenient one. We say, well, let's just say all of that was converted to that mole for mole. That means half has been converted to this at this particular point in the titration curve. Start there and then apply your equilibrium conditions. So we can do that. Here's our equilibrium conditions. We're saying that the initial concentrations are 0.05 of each. And now you notice I've changed that from a concentration. Here we got the number of moles. I converted it back to the concentration because concentrations are what you plug into equilibrium expressions. So the whole volume is still around 1/10 of a liter. So those are now in 1/10 of a liter. That means the concentrations are 0.05. So I put the concentrations in there. I say there's none of this has been produced yet because I'm saying I'm starting exactly here and then the equilibrium occurs. The change is that some of that dissociates and makes some of that and a little of that, and that will determine the pH, the H3O plus. So I want to solve for X. There are the equilibrium concentrations. I write the equilibrium expression, products over reactants, set it equal to the K. The pKa of acetic acid is 4.75. So K is 10 to the minus 4.75. You know, I do that sometimes just because it's easier to add exponents than push logarithms all the time. So I can solve that. How do I solve that? Well, I do the usual thing. These X's are probably small. It's a weak acid. These are probably small with respect to 0.05. So if I add or subtract X from 0.05, it's still about 0.05. So those two things are going to cancel, and X is 10 to the minus 4.75. And now you see why I did that. Because X is 10 to the minus 4.75, and that's the H3O plus concentration. So the pH is 4.75. Makes the math super easy. 10 to the minus pH is the H3O plus concentration. So that exponent is the pH. That's why I just left it as 4.75. Simplify the math tremendously. So you notice something? That the pH is minus log 4.75, which is 4.75. And that number is the pKa. I put 10 to the minus pKa to get the Ka. 4.75 is the pKa. So at equivalence point, 1/2 equivalence point, I got halfway there. Equivalence point, all of that is converted to that. Half equivalence point, look at that, the pH is equal to the pKa. That's something you can take to the bank. At equivalence point of a titration of a weak acid, the pH is basic because you form the base. At halfway there, half equivalence point, the pH is equal to the pKa of the acid. Super convenient little point. You get this point for free on the titration curve. If I ask you to plot a titration curve, halfway to equivalence point is the pKa. Ding, freebie. Plot that one. Okay? I hope you're listening. Someone ring a bell. Okay, moving on. Let's talk about this region that we kind of skipped over. We did A and C regions. That region is now the interesting one. We calculated the pH there. We calculated the pH there. What about the pH here? And we just did that. We went right in the middle. We went halfway to equivalence is what we just did. And we said at that point, half equivalence point, the pH is equal to the pKa. That is the buffer region, and that is the most interesting and important region of the titration curve. That equilibria is why we study weak acids and weak bases at all. This is what we are trying to get to, because we want to know what happens in solution when this situation is occurring, because this situation is occurring in your body. Your bodies are buffered. Buffer means I don't change very much. I'm buffered against change. I resist change. You can see it on the titration curve. If you add a little more base, the pH is not changing. If you had added less base, the pH is about the same. This flat region, you can add acid or base and the pH doesn't change very much. That's the value of a buffer. They resist. If you eat something with a lot of vinegar on it, you eat that that acid. Is there a question? No. If you have an acidic diet, a lot of acid coming into your gut has a lot of acid. Were that to be processed into your bloodstream, that would lower the pH, but it won't, because your blood is buffered. Your cell contents are buffered. They don't change dramatically. It has to be, because things aren't going to function in your cells if the pH is going willy-nilly every time you eat a sandwich. Okay? Depending on how spicy you like your sandwiches. So let's talk about point B. Point B is the buffer region. The concentrations, we saw that a minute ago. That's how we calculated it. We set the acid and weak base concentration to equal, and then we applied the equilibrium expression. So there's weak acid in solution, and it will react with base if a base is added. If a strong acid is added, that would send you back in this direction along the pH curve. If that is added, then this reaction will happen. And this is why buffers work. This is an exam question that it's not yet, but maybe I'll make it one. What are the Ks for those two reactions? Where do those lie at equilibrium? You should be able to tell me, because you should recognize this one as the reverse of the weak acid, or excuse me, weak base, conjugate base reacting with water to form the weak acid. This one, the reverse of the weak acid reacting with water. Those are the reverse of reactions we know have very small Ks. The reverse have very big Ks. There it is, the reverse, very big K. The reverse, very big K. Every little bit of base or acid that you add is immediately sucked up and changed to the other species. And when these concentrations are about equal, HA and A minus, the pH stays around the pKa. pH doesn't change very much. Why? Because you put a mole of strong base, it's eaten up by the weak acid is there. You put in a mole of strong acid, it's eaten up by the weak base. These guys scavenge all the OH minuses and H3O pluses and make them water. They stop the pH from changing by eating up all the acids and bases that you add. Those Ks are very, very much bigger than 1. The equilibrium lies all the way towards products, and the products are water and the weak acid. Doesn't mean the pH is 7. It means the pH is what it is with a mixture of all those things in solution. And we calculated when there's a mixture of all those things in solution, if those are about equal, the pH is at the pKa. So the pH gets stuck at the pKa for a long time. Play that back. That little explanation of why buffers resist change in pH. All that science, chemistry, all that conceptual stuff about what you know about weak acids and weak bases, the size of K, are in there. And you know that's what I like to ask you about. Conceptual things about the size of K. Don't do a calculation. Just tell me what happens if you know K is big. What happens if you know K is small? Okay? So we can do the calculation. We already did it. So we know the pH is equal to the pKa. We can write this expression, which tells us how does the pH change around the equilibrium, half equivalence. How does it change when these are about equal? Well, when they are exactly equal, so this is kind of the equation of the curve in the buffer region. The pH, how it changes with those two concentrations. So we already saw at half equivalence, those two things are equal. That's 1. Log base 10 of 1 is 0. Okay? Equal concentration of acid and conjugate base, we knew that. The pH is equal to the pKa. We did the calculation. So half equivalence, pH is equal to the pKa. If the ratio is less than 1, then that number is less than 1 and the log is negative. So I go to a pH less than the pKa. I subtract a little from the pKa. And we see that here, the pH is less than the pKa. In this region, it's the opposite. Now, the A minus concentration is slightly bigger than the HA concentration. So this number goes positive, and you add a little to the pKa to get the pH. So that's why we went through all this trouble of doing pKa's and pKb's, because it makes this easy. I know it doesn't sound easy right now, but after you get used to it, it makes it easy to tell what the pH of a buffer is and how it will change slightly if these things change slightly. If these things change dramatically, you know that I'm going to go to full equivalence, and the pH is going to change a lot. But when they're about equal, this holds. So within a factor of 10 of each other, that's going to hold. So here the pK is +1 if I do get that factor of 10. If this is 10 times bigger than that, that is 10. Log of 10 is +1. So right at the end of the buffer region, the pH is the pKa +1. If this is 10 times bigger, the acid form is 10 times bigger, then this quantity is 0.1. Log of 0.1 is -1, and you're at pH 1 unit less than the pKa. I think I'm going to run out of battery here. Somebody yell if the audio goes out. Battery's getting weak here. You guys yell from your... I would like to hear a collective yell from the ether when it goes out. There's a disturbance in the force. I sensed a disturbance in the force. If you're Star Wars fans. So here's the summary. Again, the ratio is 0.1. Your pH is less than your pKa. The ratio is 10. Your pH is 1 unit bigger than your pKa. And we can look at a demonstration of that happening. A buffer resisting a change in pH. So let's go to Lonnie. So Lonnie has 3 solutions, and the colors, there's an indicator in them. So this one is neutral. The color's about green. This one is acidic. The color is yellow. And this one is basic. The color is bluish. The indicator will change color as the pH changes. He's going to add dry ice. If you add dry ice, then carbon dioxide, that gas, dry ice is solid carbon dioxide, that gas dissolves in the liquid, and when CO2 gas dissolves in liquid, it's transformed into carbonic acid. We're going to talk about that more in a second, but I'm going to put CO2 gas from the dry ice is going to sublime. It's going to bubble through the situation. So I'm going to have CO2 gas in equilibrium with the dissolved CO2, and CO2 aqueous forms H3H, this carbonic acid, H2CO3. So there's an equilibrium between those two. Basically, you acidify a solution when carbon dioxide, a solution of water, when carbon dioxide dissolves. So I'm adding acid is the lesson here. So if you add acid, this solution should be become more acidic. This solution should become more acidic. This solution is neutral water. Now the caveat here is these are buffered solutions. So this is buffered at that pH. This is buffered at that pH. This is just water, no buffer. So let's add the dry ice and see what happens. You can go right to, are you at the screen? So there's the base. Now look at the dramatic change. Goes right to the acid form. So this buffered solution here changes very slowly. It's buffered at that pH. This solution, the other 2 solutions were unbuffered, apparently. That happened fast. Pause, stop. That happened so fast, we can... Oh, for goodness sakes, it tells me it's going to play that one. Ah, screw it. I was going to watch it again, but this is giving me a hard time. You saw the pH of two of those solutions change rapidly. The unbuffered ones, I thought the two outside ones were buffered, but I guess not. One went, pH went down, turned red. The one that was buffered, the blue one, did not change. It stayed blue. That indicator is telling you the pH is not changing. If it changes color, the pH is changing. That's what an indicator tells you. We saw this as well, too. We saw when you dilute a buffer, then both those concentrations change by a factor of 10. The ratio stays the same. And if the ratio is about the same, then the pH is about the same. So you can also dilute a buffer and it will resist change in pH. Okay. Shown in yellow is the titration curve of nitric acid, a strong acid, with potassium hydroxide, a strong base. I'm telling you those things. Which is the correct curve for a 10 times dilution? So in yellow is the titration of the HNO3. Then I'm going to dilute it by a factor of 10 and do it again. And the question is, how does the pH, how does the titration curve differ from that? So let's turn on our quiz software and you guys can respond. Maybe it'll go. There it goes. And let's take a vote. Okay, we lost sound. I'm back. So we're starting again here. I'm going to go through this. I said I agree with the A's. The vote was about equally split between A and B, slightly more for A. I agree with the A's. I'm going to draw the two solutions. Let's just say that there was, who cares, 0.1 moles of HNO3. If you have that in solution, it would make 0.1 moles of H pluses because it's a strong acid, it totally dissociates. Exactly the same amount when you dilute by the factor of 10. You still have the same number of moles of HNO3. So the concentration goes down from 0.1 to 0.01. The number of moles of HNO3 didn't change, simply the concentration. You added water. So the total number of moles of these things didn't change. The volume changed, so the concentration went down. This is moles per liter, the concentration. Liters got 10 times bigger. So this pH, how do those two pHs react? This would be pH, this is 10 to the minus 1, that would be pH 1. This is 10 to the minus 2. That pH would be 2. Okay? So that makes sense. The pH went up, but that doesn't help us because all of them, the pH went up by a factor. We don't have a scale, but went up by a factor of 10. pH went up by a factor of 1. But the key thing to realize is the NO3 minus concentration, the number of moles of HNO3 not minus, the moles HNO3 did not change. I have the same number of moles of NO3 minuses and H pluses here and here. Same number of moles. And what points do I know on the curve? Well, equivalence point is an important point. What happens here? I've added 1 mole of base. And notice this isn't volume I'm titrating by. This is moles of base is what I've given you here. It's a little easier. So these points have to be the same. I did not change the total number of moles of acid in the solution. Simply its concentration. So the concentration is lower, but this is, I'm going to go find the right number of moles of base to react with every mole of acid. If the number of moles of acid did not change, then it takes the same number of moles of base to get there, whether it's dilute or concentrated. So they're the same. So that eliminates B, and now just A or C. So A or C, the difference between A and C is the end point. The end point, you've added so much base that you just have a solution of strong base. So it's just the base concentration. So you get the pH simply from how much base you have added. So in that case, you're adding base, but this is moles of base in either 1 liter or moles of base in 10 liters. That's the difference between the yellow and the green. Moles of base in 1 liter, moles of base in 10 liters. So if you have the same number of moles of base with 10 times the volume, that's 1/10 the concentration, and 1/10 the concentration lowers the pH by 1 unit. Okay? Goodness, if you understand all that, good for you. Okay, so the pH changes by 1 unit, equivalence point, unchanged, dilution by a factor of 10, another pH unit down there. So take your screenshot there. That's a nice summary. And we'll continue. Okay, you knew it was going to happen. Let's do the same thing with the weak acid. I'll talk through this one with you. So exactly the same situation. Now I'm going to change it to a weak acid and do the same thing. Weak acid we've talked about a lot. We've already talked about what happens when I dilute it by a factor of 10. We've already talked about what happens at the buffer region and a factor of 10. Okay? So we should be able to figure this right out. So there's the dilution. So I'm saying it's C. Why is that? Well, initially, we've seen this. You take the weak acid, you dilute the weak acid by a factor of 10, the pH does not change by a full pH unit because you have that weak acid left holding back in solution. You have weak acid, HA. You had to put a lot of that in to get to the pH. There's a lot of that hanging out there. You dilute by a factor of 10, the pH doesn't change that much less than 1 pH unit. What about equivalence point? Same thing at equivalence point. Equivalence point is you've added 1 mole of acid for every mole of base. I'm sorry. We're titrating with a mole of base. You've added 1 mole of base for every mole of that you've had. It converts all of that to this. And that did not matter whether it was 10 times bigger or 10 times smaller because you did not add any more of this. Both titration curves had the same number of moles of HA. So it takes the same number of moles to get to equivalence point. And so that's the same. A and C, we can eliminate B again. A and C are still options. Why is it C and not A? Well, look at this. That it's hard to tell because we know the pH changes, but there's no units there, so we can't tell if that's 1. This one, we have it changing less. The difference between these is the pH at half equivalence is different. But that is when I'm a buffer. And when you dilute a buffer by a factor of 10-ish, the pH doesn't change. You don't change the ratio of HA to, well, let's write it the other way because that's how we write it. You don't change the ratio It's the ratio of those two things that determine the pH. Dilute those by a factor of 10, the ratio doesn't change. So the pH at 1/2 equivalent is the pKa in both cases. So that point there is the pKa of the acid. That point there is the pKa of the acid. And the pKa of the acid did not change just because you diluted it by a factor of 10. Brilliant. So there it is, buffer region unchanged, and then the same equivalence point is the same, and then the same argument. Once you're at the strong base, you're just diluted by a factor of 10, 1 pH unit. Okay, very qualitative. That means no numbers were involved there. And you know, I like to not ask you about numbers. I ask you about the concept, the qualitative part of it. So that is what you should focus on. Okay, which of these, when added to a weak base solution, NH3, forms a basic buffer? So you put NH3 in solution, you get an equilibrium of those two. Initially, it's more base because it's a weak base, but as you add something, one of these, how do those ratios change when I add those three things? Okay, let's talk about that one together as well. There's the reaction that we're interested in. It governs the equilibrium between those two things, the weak acid and its the weak base and its conjugate acid. You add NaOH, and that's a strong base. That means that breaks up completely into OH minuses. So this is essentially like just adding OH minuses. This is essentially like adding Cl minuses and Na pluses, and in this case too, sodium plus doesn't do anything. Sodium plus, neither does Cl minus. Here, it's just like adding H pluses because that's a strong acid. So if I got this here, I add a strong acid to it, it makes more of this. If I add a strong base to it, then these would be used up. Any amount of those that were there would be used up. This solution will be a buffer around 5 because the pKb of this is 5. So it will buffer around pH 5. How do I get to a pH greater than 7? How do I get to the basic form? Well, that's the basic form. I need to go in this direction. But even in the buffer region, it's a pH below, it's pH below 7. I need to get to a pH above 7. So I have to say, how do I get it to the basic form? So I can apply, oops. Sorry. What was, oh, wait, it was originally, I think I'm answering the question wrong. Let's go back to the question, the pH. I want the, how do I get a basic buffer, a pH greater than 7 in this? How do I get a basic buffer solution from an NH3 solution? You can't. Your buffer is at pH 5. To get a buffer at all, you have to add acid. What did I change this one or something? This is the buffer. When these two concentrations are equal, the buffer and the pH will be 5. That is, oh, I see. The original solution was, the original solution had a pH greater than 7. Is that what I think that's what I messed up. The original pH was greater than 7. How do I get it to a buffer of 5? Well, if the initial pH is greater than 7, then I have to essentially add acid, and I will get these two concentrations to be equal. And when those two concentrations are equal, adding acid converts that into that. And the concentrations, when those are equal, becomes pH 5. And that is an acidic buffer, pH below 7. So HCl does that. That was just poorly worded. Look at all these typos all over the place. Go back and change that one. I apologize. The science we understand, the wording we did not. So this came up already. What if your acid has more than one acidic proton? If I have more than one acidic proton, here are some examples. That carbonic acid, that's what happened when we dissolved carbon dioxide in water. Phosphoric acid, H3PO4. Sulfuric acid, H2SO4. Those two relatively weak acids, that one a strong acid, especially the first proton that comes off. Well, it's actually easy to sketch the titration curve. pKa's always increase for each proton that you take off. And that should make some sense to you. You take off one and the species is going to become negative. How are you going to pull another positive charge off that? That gets harder. And another positive charge off that. It gets more and more negative. So it's harder to pull off successive protons from a polyprotic acid. So the pKa's go up. You get weaker acids as you pull off protons. let's look at the example. So here's the first equilibrium, acid-base equilibrium. One proton has come off. And you have an equilibrium between weak acid conjugate base. I haven't written the rest of the things. The important thing is that is the equilibrium that's happening in solution. Those are the predominant ions in solution when the first proton is coming off. When the second proton is coming off, then those are the two species you have to worry about. Okay? So the pKa for this equilibrium, 6, the pKa for that equilibrium, 10. And we use that fact, we get a free point on the titration curve. If we sketch out titration curves, we get a free point. Take that to the bank because that will be on the final. You get a free point on the titration curve. You know how to sketch it because at half equivalence, pH is equal to the pKa. You get that one. Don't have to do any calculation. So draw out your titration curves and you'll have 2 equivalence points. First, you'll use up all those protons and get 1 equivalence point. Then you'll use up all those protons and get another equivalence point. Halfway, the middle of the buffer region, the pH is equal to the pKa. So I can sketch out the titration curve. Here's pKa1, the middle of the first buffer region. Here's pKa2, the middle of the second buffer region. Here, those two concentrations are equal. You've gone to half equivalence. Here, those two concentrations are equal. So relatively easy to understand polyprotic. If you understand, just apply the same thing twice. So which carbonate species is present in the highest concentration at pH 7? So here are the 3 possibilities. If the pH is 7,
2 quick questions.
Okay. Yes.
So first question is, does the half equivalence point mean anything for strong acids?
Okay, so there's some questions coming in from chat. Thank you. The question is, does half equivalence mean anything for strong acids? Strong acids do not buffer. Half equivalence is still, you've added 1 mole of base for every mole of acid, but you don't have anything there to make a buffer. You have water and your ion. So there is no buffering capacity. The definition is still the same. And the curve flattens out, but just barely. The titration, if you looked at strong acid and weak acid titration curves, so here's the weak acid, and the weak acid has that very flat buffer region. The strong acid, not so much, okay? So there's not that buffering capacity where the pH doesn't change very much. So short answer, strong acids do not form buffers. They do not have this flattening of the pH of the titration curve.
And the second question is, wouldn't the pKb yield the pOH value, not pH?
Yes. So the question is, does pKb yield pOH? No. Those aren't directly related. So the question is, does pKb give you pOH? Does it give you the pH? Only at one point, when the acid and conjugate base are in equal concentrations. So pKb is minus log of Kb. pOH is minus log of OH minus. Those two things are not necessarily related. Okay? You would have a relationship. The pKb would be equal to the pH at half equivalence of your titration. And you could show that. But these two things are just two different, those are two different things. This is a constant. This is something that changes during the titration. They're coincidentally equal if this is H3O plus at half equivalence.
You're saying this was for the last one, the one that was about like adding a buffer or something.
Yeah, we did. Oh, did I write the pKa?
PKB.
The pKb determines, pKb would determine this point if it were going, if it were going down like this. So if you started with a base, then pKb would determine that. Is that what was wrong with the yeah, okay. I don't have time to go back to that right now, but yes, if let me just write it here. On that last chem quiz, if NH3 concentration and NH4 plus concentrations are equal, and you start here with the NH3 and you're adding this, then the equivalence point, half equivalence point, is where the pH equals the pKb. And that would have been around 9-ish because the pKa was around 5-ish. Yes. It's still, okay, I have to go back and rewrite that chem quiz because it still seems like there's a typo in there somewhere. But let's do this one. So we understand those things. There's no direct relationship between pKa and pOH except at the half equivalence point. That's just a coincidental pKa equals pH. That's the coincidental relationship. The relationship between and the other question was I forgot what the other question was. So let's talk about this one. Which carbonate species is present in the highest concentration at pH 7? So we need to find pH 7 on the titration curve qualitatively. So let's do that. So here's the titration curve. This equilibrium predominates at pH 6. This equilibrium, those two things are equal around pH 10. So we're somewhere between those. So this is pH 10. This is around 10. pH is equal to the pKa at the half equivalence there. This is around pH 6. So we're somewhere in between those two. And the question was, which predominates at pH 7? So pH 7, oh, there's probably an animation for that. pH 7 is 1 unit there and 3 units away from there. And you know that with this range, the buffer range, this extends from pH is too small to do this, but the end of the buffer region is pKa plus 1 in pH, and the beginning of the buffer region is pKa minus 1. So pKa plus 1, that's where we are. We're at pH pKa plus 1. You're getting near the end of that buffer region. And that buffer region, these two things are in equilibrium, but you're getting near the end of it, so you're getting more HCO3 minus. So HCO3 minus is present in the highest concentration there. And it's present in the highest concentration all the way up till there, and then these two are in equilibrium. So then there's an equal amount of these two. Okay? So here's what's interesting to you guys who are in biology is why, we keep saying it, why is this so important in your body? This is one big reason why. all the proteins in your body are made of amino acids, amphoteric compounds that behave like acids and bases. They have that amino group that we've been talking about forever. And they have that acid group. They have one of each. So they have that weak acid that we talked about, NH3 forever, that COOH group, that weak acid group. So all the amino acids in your body, all the proteins in your body, they have these groups that have pKa's associated with them. They're weak acids or weak bases. So I've written the pKa's of the acids. Now, when I write a pKa, I'm talking about the acid form. So I'm talking about a proton coming off. That proton comes off around pH 2. That proton comes off around pH 10. Now, what do I mean by comes off? I know at pH 2, this equilibrium, at pH 2, there's an equal amount of the COO minus and the COOH, the acid form. There's an equal amount of pH 2. So at pH 2, half of the protons have come off if you're starting from low pH and going up. If you get to pH 3, then there's 10 times as much the base form. So pH 4, 100 times the base form, and then it starts to not obey that equation very much anymore. But as you go by the pH of this pKa, as you go by that pH, pH 2 is when it comes off. The proton is being removed here. That proton is being removed at pH 10. It's half on and half off. Half the molecules have it, the other half don't at pH 10. Here, half the molecules have the proton, half of them don't at pH 4-ish. So that's why I say that's where that proton comes off during a titration curve. As I'm pulling off protons, that proton comes off around 2, that comes off around 4, that would come off around 10. That means it's on below 10. This is on, pH is on below 2, and this proton is on below 4. So I've written it at pH 7. So that's below this, proton on. That's why I've written it with the proton on. pH 7 is above this one. That proton comes off at 4. By the time you get to 7, it's all the way off. And this proton comes off at pH 2. By the time you get to 7, it's all the way off. So you can write, and that'll be a question on the exam, just tell me what the charge is on an amino acid at a given pH. And you just look at all the pKa's and you say, is that proton on or off? It's vitally important for the chemistry in your body. How your amino acids are charged determines how your proteins work. So the pH matters very importantly. Here's 2 more, lysine and tyrosine. And you can see many places to be protonated. So they're polyprotic and amphoteric compounds. Don't have to worry about that word. So why is it so important? Here is the structure of a protein. So this ribbon thing is just a cartoon. It's just a picture of the long chain of amino acids. So all those amino acids link together, they polymerize, and they form your proteins. So this is a long chain of varying, there's around 20-ish amino acids your body uses. They form these long chains. And then the long chains form these beautiful complex structures. And those beautiful complex structures is what allow the protein to work. And here you can see there's this molecule. Can you go to just the screen so they can see? Just in here, there is another. This is a separate molecule right here. And that molecule is involved, this protein catalyzes a reaction of that molecule. That's a substrate. So that goes in there, and there, actually, that might be a cofactor. It doesn't matter. That fits in there because of the structure of this. I don't know what it is off the top of my head, but that's probably a cofactor and not the substrate. You don't have to know about that. The important thing is that fits there because of the way this folded up. And that's how proteins work. They can clamp onto things, other molecules, because of their structure. And what helps them form that structure? Well, it's the charge state of the amino acids. If you have little pluses, minuses along that's called an alpha helix. If you have those pluses and minuses along that alpha helix, that can hold that alpha helix in place. If you have hydrogen bonding, because you have a proton here and a slightly negative charge here because of the pH, hydrogen bonding holding that in place. So vitally important for your protein structure. And we'll talk about that next time and show you a demo of how we can blow that guy apart, that horseradish peroxidase. So we'll see you next time, Tuesday. Look for some announcements today about the final and other important things for getting ready to end the class.